All right, so I am Matteo Pasquali from Rice University, and I will moderate the second part of the morning session, which is on energy storage technology. And our first speaker is Dr. Gregory Bowthorne, Professor of Physics and Environmental Science from University of Oregon.
Okay, my task is to give you a brief but hopefully comprehensive and only slightly biased view of the current state of energy technology, storage. And in keeping with the theme of speaker diversity, in my real life or in my spare time, whatever, I can't tell the difference between the two, I actually do astrophysics and cosmology. Therefore, feel free to ask me any question you want about how the universe works, because I think I understand that a whole lot better than I understand our current energy policy. So if we think about energy storage and think about scalable solutions, let's draw a little diagram of what this might look like. Well, we have two issues. We have grid capacity and we have grid reliability. We need to feed the grid with some capacity, so we make some power plants. Don't care what they are right now. And we've fed the grid. And then we have some exchange mechanism, some opaque black box, which tries and delivers electricity reliably around the country. And that works more often than it doesn't, so that's good. Now we have a new player that we don't quite know what to do with, renewable energy. How does that fit into this parallel grid capacity, grid reliability scheme? And then we have storage. What are we going to do with storage technology? What are the economic incentives? What are the technological incentives? How do we use this in this infrastructure? And the most straightforward way is to just bridge grid capacity with storage and have somehow the grid constantly talk to a black box storage mechanism and then grab energy from the storage mechanism when it's needed. But maybe we should be a little bit more clever than that. Maybe we should use storage to maintain grid reliability so that everybody gets some electrons, at least at some point in the day. But we haven't drawn any connection with renewable energy yet. It's still a floating icon there. And the traditional pathway would be, well, let's just add it to the power plant supply chain to feed the grid. Well, yeah, we could do that. There's infrastructure problems and technology problems. But maybe we should be slightly more clever and think about using renewables as dedicated means of producing energy storage. So the key points I want to get across today are, I want to define a quantitative objective goal, 10% 1 hour goal, and I'll go through what that is. I want to give you a brief conceptual overview of energy storage. I want to say, okay, we got all these choices. What's a sensible way to evaluate this choice matrix? Give you some specific examples of current technologies. And finally, at the very end, I want to talk a little bit about using hydrogen as a proxy for transmission lines in the guidelines of energy storage. So what's this 10% 1 hour objective? Well, if we look at our electricity demand as a function of time, it of course continues to rise. And in 2005, we used approximately 3,600 billion kilowatt hours, a really terrible unit, especially if you're a physicist, because billions and thousands together is something else. But nonetheless, it's a unit, so let's distill it down to the following objective. I want a black box storage thing which will supply 10% of this energy to the grid for 1 hour. That's my goal. What's that mean? I need a black box that's really a hell of a big battery, 50 gigawatts for 1 hour. That's what I want to meet this goal. On a more personal scale, we can couch this goal as follows. Every individual American, whether you like it or not, is using 1.5 kilowatt hours of electricity every hour, period. So, if you want your personal energy storage device, that equates to you require something that's going to give you 150 watt hours of electricity for 1 hour. Well, what's your choices? Well, you could walk around with a 2 to 4 kilogram battery pack, or you could walk around with 10 grams of gasoline in your pocket. That's the problem with energy storage. It's a lot in carbon. It's not very much in materials. And it also shows that our consumption scale is large. So the proper plan is to develop in parallel new technologies for generation and storage while somehow reducing or at least leveling consumption. If we do both of those things over the next 50 years, we can actually be a sensible planet. What do we need energy storage for? This is pretty obvious. You'd like a black box to turn a switch on and say, I need more energy because region X has got a big peak load, so give it to me. Smoothing over to the demand fluctuations. Obviously, energy storage is an important safety net for intermittent energy suppliers such as wind or biomass or seasonal hydroflow. I live in the Pacific Northwest. It doesn't snow there anymore, so we have to buy our power from somewhere else down the road. Not good. You can use it as a means of recovering waste energy. That's not very interesting. But perhaps another driver for this is the regulatory climate, which is going to demand increasingly higher grid reliability. And so we want a safety net mechanism so that the grid is 100.0% reliable. That would require some magic battery somewhere that we could flip a switch on. Well, I'll also remind you, whether you like it or not, that our future energy plan, as devised by the current federal government, is to basically continue exporting lots of money on a daily basis overseas. And we're just going to use liquefied natural gas instead of oil, with 45% of the remaining reserves of natural gas being in Russia and Iran. Nice combination, but that's what the planet has left us at this point. And we have to import this, but we don't have any infrastructure for importation. We only currently have 4 LNG terminals, and the plan is to go from 4 to 44 by the year 2020. And that's just sort of repeating the sort of dependence that we have on importation of fuel as an energy source. And it really shows we haven't learned very much, unfortunately. But this has got a lot of momentum, so it's unlikely to be overturned very easily. But let's take advantage of it. And this is what's happening on the drawing boards in Iowa. Practically 2/3 of the natural gas that's used in a gas-fired compressor to make steam goes to drive the actual compressor instead of heating the water to make the steam. Well, let's try this. Let's use some wind energy out there in Iowa, where there's a lot of it, and charge up a compressed air storage system and pretend we can store that underground in some aquifer. And we're going to feed that compressed air to the compressor, thereby reducing the load of the natural gas fuel supply on the natural gas-fired electricity plant, because we've got another means to drive the compressor. Now, I'm not here to argue for or against the merits of this, but I'm just here to point this out as an example of here's something that actually integrates everything together. You have conventional fuel generation from fossil fuels that's being supplemented by renewable energy that's using some kind of energy storage as a buffer. And the more we think about combining things, combining technologies, I mean, the end product is you want electrons coming out, and there's lots of ways to do that, so why monopolize it on a per-site basis? Just use everything you can think of to reach the end goal. And so this is a good example of a potential integration. Now, let's go off to the Walt Disney power plant here. This is the 1,000-megawatt power plant, non-polluting, where everybody's happy. And we'll pretend that this power plant has the luxury of operating at 80% capacity for 50 straight days. Now, this is probably true 10 or 20 years ago, but probably no longer applies today. Well, let's just pretend. I mean, it's Disney World, so we can pretend. I tell my students a lot about Disney's first law. You probably never heard of Disney's first law. Physicists talk about the first and second law of thermodynamics, and there's the economics law of supply and demand. But it's really Disney's first law that seems to drive everything. And Disney's first law simply says, wishing makes it so. So here we have our wishful power plant, and we're running at 800 megawatts to deliver to our customers. We do that for 50 days. So I got an extra 200 megawatts that I can charge up my energy storage system. Well, let's assume I can do that at 90% efficiency, and I can with some technologies. So I get some number of megawatt hours of storage. That means that if I can recover that, I can now run my power plant at 200% capacity for 9 days. Now, that's a reasonably economical strategy for trying to invest in energy storage at the site of production. But it doesn't make any sense if you're running at 100% load. So this will vary from site to site, but this is the kind of framework that you would need to manage peak load with energy storage. Demand, of course, is increasing. We saw the situation in New York City. That's just the state of Utah there, but I'm sure this is true regionally. The megawatt differential between average demand and peak demand is growing every year. That's not good. that problem has to be solved. Maybe it can be solved by real-time pricing and consumer behavior, but I don't think consumer behavior is ever going to solve anything personally myself. So I think this is a managed problem. I think energy storage can really plug into this differential between peak power and average load in quite an effective way. And of course, peak demand is becoming climate driven. I could give you a talk on climate change if you wanted, but I won't. I'll just remind you that the climate is becoming increasingly volatile. Temperature extremes are happening now on a seasonal basis, and a lot of the peak average differential demand is growing because of extreme climate. That's probably somehow coupled to our overall energy generation problem. I mean, the Earth is a closed system. It does talk to itself. So what are our choices in estimated costs? So those are all the things I'll describe briefly. I'm sure you know what all those are. Lithium ion just means advanced battery material. And if you want to do estimated costs, you can say, okay, well, how many dollars does it take to produce this many megawatts of energy storage? Or how many dollars can I meter my energy rate that I get out of my energy storage, in other words, kilowatt hours? And I'll just click through these fast. And the point is the following, that whatever the technology is, the actual capital cost of the construction in dollars per kilowatt doesn't have a very large dynamic range. But the actual energy delivery cost has a very large dynamical range because some of these things don't discharge for long time scales. You can charge up an ultracapacitor and you can get some energy out for a few seconds. So it has a very high energy rate. And if you look at this, there's only two technologies, unfortunately, because they're very site dependent, that have high cost effectiveness in terms of energy cost. $12 a kilowatt hour for pumped hydro and compressed air storage. Everything else has a fairly high cost. And so all of this becomes some kind of complex economic calculation on a per generation site basis. Does it make sense to invest in some energy storage technology here and there? And at the end, I hope to try and convince you it makes some sense. Now, the traditional way to talk about energy storage is to plot specific power versus specific energy density. And this is kind of that plot, but it's a little bit different. And you can see that in the upper right-hand corner is where you want to be. You want things that have high system power that can discharge that power for hours timescales. There's only two things out there, pumped hydro and compressed air. But there's this flow batteries up at the top there that is a very interesting technology. It's a very old technology. It's a very simple technology. We seem to run away from simple technologies a lot. There's a lot to be gained by just trying something simple first. And the flow batteries have the interesting advantage is that they can be designed, because it's just volume of electrolytic fluid, to have fairly large capacities, and they discharge that capacity over the hour time scale. They're actually one of the only scalable energy storage technologies out there. But this diagram is just meant to show you that whatever your choice is, and you see SMES at the bottom, superconducting magnetic energy storage, lots of power, discharge very fast. There's a huge dynamic range in this power storage differential versus discharge time. So all technologies fill out different regimes in this matrix. Now, pumped hydro is incredibly simple in principle. Pump the water back uphill. And one of the biggest facilities that's grid connected in the country is quite impressive. It's in Ludington, Michigan. It uses Lake Michigan as a lower reservoir. The upper reservoir sits 75 meters above Lake Michigan. And it has 2,000 megawatts of total capacity. And when you pull the plug out, it takes 8 hours for the water to discharge. So that's a pretty aggressive energy storage system that you could directly connect to the grid for a few hours. But there are not many places in the world that have a large body of water sitting above another large body of water. And so site is physical, geological characteristics of your site limits pump hydro. There's 300 pump hydro systems in the world, and there's a couple dozen in the United States of capacity 1,000 to 2,000 megawatts. Now, we all want better batteries because we want our laptops to last more than 2 hours. And so we're moving toward the goal of 400 watt hours per kilogram by something called lithium polymer. That will be a good personal energy storage device, but probably doesn't have commercial or industrial applications. Flow batteries, simple idea. I got two electrolytic fluids. One's got negative ions in it, one's got positive ions. Hey, that's a big battery. Separate out, that's electric potential. Wow, I can get energy out of that. You know, it was just thought of 100 years ago, but it's been ignored until recently. And this is fully scalable. If I want more energy, I just have more volume of fluid, and liquids are more scalable than solids or gases. Just pour more in a container. There you go. And here's an example, hypothetical. This was supposed to come online in the UK in August of 2003. I don't know if it actually did. But in principle, you can just engineer this into your building. So here's some building. There's a pizza delivery van coming up to the employees in the building that are, working after hours or whatever. And so that's the scale. And behind the building are a couple big storage tanks. And we're all used to seeing storage tanks. And we always wonder what's actually in these storage tanks we see. And in this case, it's just simple electrolytic fluid that's got a total capacity of 15 megawatts. And the discharge time is 8 hours. So this building could probably run by itself for 8 hours on its own little flow battery. It's not so little, but it's part of the building. So I'm trying to push on our own college campus, the University of Oregon, and we'll paint one of the tanks U and the other tank O, and stick it behind our football stadium. And I'm serious about this because the more students see renewable energy generation demonstration projects on their campus, the more energy will impact them. So putting solar cells on your student rec center, your student center, and a little interface so the students can read what's going on, the more you can do these things, the better. The Rice Biofuels Club is an excellent example. So everybody go back and build some flow batteries for your business or your industry or your campus. It's not too expensive. Flywheels. NASA loves flywheels. Why? Because advanced materials can give you 900 watt-hours per kilogram, 3 times better than the energy density storage of batteries. When you fly in space, payload matters, so you want a flywheel battery rather than a standard battery. More on flywheels in a moment. I know nothing about Beacon Power. They just had a nice view of their product on a website. And so this is a 25 kilowatt-hour unit, and you can see the discharge profile, and it shows that you can get 200 to 100 kilowatts of power that's discharged over 5 to 15 minutes. The physical footprint of this is small. It is a 60-inch high cylinder and a 36-inch diameter flywheel. It weighs 3,000 pounds, so that's a lot. But physically, it's not much of a footprint, and so you could fill this room up with a whole bunch of these things, and that would be a pretty good energy storage system. Compressed air, great in principle. It's just a big scuba tank, but you need something to hold the compressed air. And so you need a natural cavern, like a limestone cavern or a salt cavern or maybe an aquifer. And the manifestation that this isn't easy to do is that there's only 2 sites in the world to do this, one in Germany and one in Alabama. Superconducting magnetic energy storage, which we heard a little bit about yesterday, I think can have reasonable utility scale applications. The energy density depends on the square of the magnetic field. So that's a material property, and this mu, which is a magnetic permeability, also a material thing. Material scientists are incredibly clever, by the way. Never underestimate their power. I do think you're going to see tremendous advances, at least on the 20-year time scale, for superconductivity. So there's a sort of industrial scale application. You have some coils down there, which may be 12 feet high by 8 feet in diameter, so you can stick that in a building on your power plant. That can store up to 1,500 megawatts of energy, megawatt hours of energy, and that's good for utility scale application. And the key here is getting materials that don't require cryogenic cooling. If your superconducting coils have to sit in a vat of liquid helium at 2.7 Kelvin, that's not cost effective. If your superconducting coils can just sit out in the air at air temperature, it's tremendously cost effective. So I think superconducting magnetic energy storage really does have a future in utility scale applications because you can dump a lot of power on the grid for a few minutes. Now here's just some kind of matrix comparison in which I've isolated 3 quantities: the power, the economy of scale of power that you would build this thing at in megawatts; the efficiency, that's the efficiency of turning excess power into energy storage, and it's all relatively high in these systems except for compressed air because you've got to deal with the ideal gas law and other physics problems you can't really get around; and the discharge time in hours and minutes or seconds. And the only point here is not to say somebody wins and somebody loses. It's that each technology carries with it a different array of power capacity, efficiencies, and time. So depending on your application and your site, you can pick your technology. So how do we integrate these technologies with my 10% 1-hour solution? I want my 50 gigawatt hour battery. How do I get it? Well, I could build 25 of those Lake Michigan Ludington reservoirs, grid connected. That's a big engineering project, but we built Grand Coulee Dam during a downtime in our economy, and that was a big engineering project, so it's not out of the question that one could do that. You could have 100 million kilograms of advanced batteries, and if you want to take a number away with you from this conference, it's the one in parentheses. You need 1 billion kilograms of AA batteries to be able to charge up the grid at 10% for 1 hour. So that should scale what our consumption actually is. There may actually be 1 billion kilograms of AA batteries distributed in Walmart stores in the country, actually. So perhaps it might work. Or you need 300,000 grid-connected fused silica flywheels of radius 1 meter and width 1/4 meter. 300,000 is not a large number. You could count to 300,000, on your fingers in 24 hours. So that's not a big number. So that's a doable project in principle if you wanted to do that. Or you could build this hell of a scuba tank, 300 by 300 by 300 cubic meter of compressed air that you want to get out in 1 hour. I think that's kind of dangerous, but at least physically, you can do that. Or maybe we can do this with some form of hydrogen production. Well, this solution requires 200 million liters of hydrogen. Now, 200 million liters sounds like a lot of liquid to manage on a daily or weekly basis, but let's put it in perspective. We're currently processing 400 million gallons of gasoline a day as a physics input to our global climate change experiment. So 400 million gallons a day is a fluid transaction that's going on. So we have a distribution system that handles this and processes it. So what's 200 million liters compared to 400 million gallons? Big deal. Well, how do we get 200 million liters? Well, let's do this. So there's not much in western North Dakota, not many roads. It's very difficult to hook up transmission line infrastructure. And at $2 million a mile, your local utility company frowns on long-distance transmission lines. I know this is a major concern of the Bonneville Power Administration. So let's try this. Let's build 10,000 1.5 megawatt wind turbines and factor in some duty cycle for how fast the wind is blowing on a 24-hour day. What's the efficiency through electrolysis of making hydrogen and liquefying it? And you end up with, in round numbers, that these 10,000 wind turbines would produce the required 200 million liters of hydrogen every 24 hours. That's a large yield. And 10,000 windmills isn't very much. It's not a gigantic footprint on the land. So now, conceptually, we have an interesting mechanism of producing liters of liquefied hydrogen, passing them out to every American for their personal energy storage device to plug into the grid to, manifest real-time pricing and make money. So, sounds good to me. You could do this in the Aleutian Islands or wherever. There's lots of this so-called ambient energy, and there was a lot of it yesterday in the atmosphere around, and today it's windy and sunny. So somehow we should just build the interface to produce liquid hydrogen for storage and start distributing that. So the overall conclusions to this are the following. Electricity plus water gives you hydrogen. A lot of electricity around, a lot of water. We should start really thinking seriously about, on a 20 to 30 year time scale, how about making hydrogen an essential part of the energy storage matrix. Superconducting magnetic energy can become a utility scale application on short time scales, and I think that shouldn't be underestimated, and I think this will only get better with materials development. For in-situ industrial applications, flow batteries or small flywheel farms may in fact be quite practical, and I suspect to see more of that. But the bottom line conclusion is the conventional energy storage solutions I've talked about, pumped hydro, compressed air, advanced batteries, and the like, simply do not scale well enough to solve this increasing gap between average and peak loads. We've got to develop new technologies, integrate things together in a more scalable way, and seriously think about these dedicated hydrogen production facilities, because they do represent a physics-based solution to this problem. And I thank you for your time, and I beat the flashing red light.
Thanks for the very interesting survey and incredibly amusing anecdotes, which I will really have to steal from you, but that wasn't the source of my question. What source of my question is that I'm interested in the economics of different storage technologies. And, you know, I'm willing to substitute 5 cents a kilowatt hour PV for your wind or solar thermal for your wind. A lot of renewables produce electricity, so it's a nice synergy there. But I'm afraid of the economics. I'm really afraid of the economics, what that might do to the real price of electricity.
Oh, God, I got to ask an economics question. I think there's two answers to this. For the individual residential customer, I think that there might be some economic reward for that. Suppose that you could go to Sears and, you know, buy, you know, a 500-pound advanced battery storage system, which would store, you know, on the order of a few kilowatt hours of electricity. And it's basically going to be about the size of your heat pump. And you've hooked it up to the solar shingles on your roof. I suspect that the economics of that does work out on a consumer level when they sell that back to the grid during times of high pricing for electricity. But I agree with you on the utility scale, and I think you have to go back to the Walt Disney example, is that that's the example where it makes sense. And to the extent that most power plants are probably running near capacity these days, because we haven't really added power plant capacity yet at the rate to keep up with demand, most probably power plants aren't in that economically viable situation of shunting off some spare electricity into an energy storage system. So I think that's the limitation on the utility scale.
Your suggestion of hydrogen being a storage medium also would imply that we're able to make it happen as a distribution system, pumping hydrogen from wherever you make it to where it needs to be used is quite a chore, as is the people who are promoting the use of it in transportation are finding out as well. Yeah.
Well, I agree that there are several problems with onboard storage, with distribution of liquefied hydrogen, and it's not a problem you solve overnight. I think somebody used the Apollo moon landing as an example, and I think it's the same sort of level of commitment. If we had a goal that by the year 2020 we wanted a third of all vehicles to run on hydrogen, I don't care if it's 2020 or 2030 or 2040, or a goal to have 25% of all electrical production come from distributed wind farms, we could grow the infrastructure to meet that goal in precisely the same way we produce the infrastructure to get to the moon, and in precisely the same way that we have the current infrastructure to process 400 million gallons of gas today. So it's a matter of will and commitment and recognition that we need to do this for future viability. Now, if we can't generate that kind of will or that kind of political leadership, hope no one's listening, then whatever technologies we design aren't really going to matter because we don't have the means to do it. So I'm optimistic because I know that the U.S. can do large-scale infrastructure projects. We did this in the 30s. This is the same kind of climate. We got a problem. We've got to build we got to build a smart energy grid. We've got to have new production and distribution facilities. And given enough time and commitment, I think that can be done. So I think all this is achievable. It's just not achievable tomorrow.
Again, in the interest of time, we should move on. And our next speaker is Michael McDowell, who's a program manager, solar power systems at Pratt & Whitney. And he'll talk about solar power tower technology, large-scale storage, and dispatchable solar energy.
A couple comments to start out. Got to clear up one dichotomy that's going on about what company I work for. This name tag says Boeing on it. That used to be true. It's no longer true. The Rocketdyne division of Boeing was sold to UTC about 2 months ago. So now we're part of the Pratt & Whitney company. So that, what that says up there is correct currently. I'd also like to thank Otto Glaser for his help in getting me here. It's most appreciated. Thanks. So this is where I'd like to see part of our energy system go, to large scale. By large scale, I mean utility scale power plants that run on solar power. Talking about units of 100, 200 megawatts electric with thermal storage so that I can dispatch the power whenever it's optimal to put it out on the grid. At Rocketdyne, our main product is rocket engines, and we've been doing that for NASA since the beginning of the space program. We currently produce the liquid rocket engine that is at the back end of the space shuttle, and Delta engines for putting satellites in space. The technology that comes out of that is something that I find very valuable in advancing the solar technology. It's people who understand high temperature materials, people who understand how to weld thin sections and make complicated devices as a result of that, their rocket engine experience. We've also got energy heritage. We built the first nuclear reactor that put power on the public utility grid with the sodium reactor experiment in the 1950s. We were part of the liquid metal reactor development up through the 1990s. Part of new production reactor programs, and we're working on Gen 4 reactors. We've also been applying that energy heritage to solar power, and that's where we get a lot of understanding of how to deal with low vapor pressure, high temperature materials. In the solar power system, we use molten salt. In the liquid metal reactor program, we use sodium. Very similar in their physical properties. Chemistry is a little different. But when you know how to handle one, you pretty much know how to handle the other. We've looked at different solar technologies, and I've been involved in developing the dish engine system in the past, no longer working on that. And we've also worked with fossil energy in coal combustion, gasification, and hydrogen generation. And those are ongoing technology programs where, again, rocket engine technology is helping us advance the technology quite rapidly. But getting back to the solar power system, let me talk a little bit about how this system works. The heart of the system is a tower. We're talking about something that's going to be about 300, 400 feet tall. It's going to have a thermal receiver at the top. It's going to be surrounded by a field of heliostats. These are mirrors that track the sun in a way so that the sun is reflected onto the top of the tower. We take molten salt, comes in from the cool tank or the cold tank. That's a relative term. It's 550 degrees Fahrenheit coming in, but it goes out hotter, about 500 degrees Fahrenheit hotter at 1050 degrees Fahrenheit, and goes into a hot tank. What we've done really is separate two processes: the process of collecting or gathering energy from the sun from the process of generating electricity. Because now the next part of the process is I feed the hot salt out of the hot tank into the steam generator and turn that into electricity. So what it allows me to do is to be able to operate this power generation, the electric generation part, completely independent of the period of sunshine. I can operate 24 hours a day, or I could operate over a fairly short period of time to meet whatever criteria maximizes the value of the electricity to the grid. We think that over the long term we can get prices down to 5 cents a kilowatt hour on a standalone basis and down as low as 3 cents if we put it in a hybrid configuration with another fossil plant. This chart allows you to graphically see what's going on with a 24-hour-a-day operating plant. We're showing 2 days of duration here, sun coming in 2 discrete periods. During that time period, we're recharging the storage system. At the same time, we're generating a flat profile of electricity. At night, we suck out power from the storage facility and keep generating electricity. Now, there's a number of CSP technologies that are fairly viable and in serious commercial development. This chart shows the 4 that I think are really relevant here. The only one that has storage is the power tower. The troughs certainly have the advantage of the most large period of commercial development. There's over 340 megawatts of troughs that are currently operating in Southern California. They use oil in the field. They do not have thermal storage as part of that technology. There is one 50 megawatt plant that's going to be built south of Las Vegas, so that the key advantage they have is the technological maturity. The dish has the advantage of being fairly high temperatures and high efficiencies. It doesn't have storage. It uses a Stirling engine to generate the electricity, and there's some severe reliability problems and cost problems that need to be overcome to develop that. CPV, I think, has a lot of potential over the long term for remote sites. Fairly good efficiencies can be achieved there. Significant work needed to commercialize that system. It does not have storage. The thermal storage system is really pretty cost effective. It's only 8% of the power plant cost. We've got a low-cost storage media. Salt is not very expensive. And the tanks, even the tank that runs at 1050 degrees F, can be done with essentially conventional tank construction materials. For the losses are very low. We'll lose about 1% of the energy over a day. And it's interesting that the thermal storage can actually reduce the plant cost, because if I operate longer than an 8-hour solar day, distributing electricity, say, over 12 hours or 24 hours, then I've got a smaller electrical generator, and the electrical generation system then costs less. And the trade-off is such that you get a net less cost when you increase storage and decrease the size of your electrical generation system. Also, we probably can get increased electric value depending on the pricing structure that the utility has. And we've been talking a lot about the pricing structure earlier today. I do note that this is probably not the right storage medium for storing power that's already in the form of electricity on the grid. That the energy conversion efficiencies in going back to electricity are not as good as some of the other storage mediums that Greg was just talking about, but it works really well when we've got a system where we're gathering energy as heat and we can store it before turning it into electricity. Because this program is oriented on storage, I put in a little more information into my presentation on the storage medium. This chart compares several different storage fluids that could be used, that have been explored for use in this kind of plant. Solar salt is what we use. There's a high-tech salt, high-tech XL, lithium nitrate, that are different salts that could be used. There's also thermal oil, and that would lend itself for use in a trough plant, possibly. We've selected the salt because of its good physical properties and because of its low cost. One thing we really want to do is get a fluid that we can operate at a fairly high temperature and get good electrical conversion efficiencies to take advantage of the very high temperature capability that the tower has, because we get a lot of solar concentration off of the tower. So we've got, for the solar salt, an upper limit of 600 C, and that gets me the conversion temperature that I'd like to have. What happens above 600 is it starts to come apart chemically. We've got a freezing point of 220 C. That's, yeah, I'd prefer to have something a little lower because freezing can be a problem, but we know how to handle that on an engineering basis, and so we go with that. Solar salt has a very high heat capacity, but also really importantly, if you go down to the chart at the bottom, solar salt is a very low cost, and combining that with the conventional structures of the tank gives us a thermal storage system that's very cost effective. Talking briefly about the increased electricity value, this is a chart put together by Brandon Owens, who was at Platts Research and Consulting at the time he did this, and he was looking at if we had a 100 megawatt electric plant with 4 hours of thermal storage, what difference would it make? And he came up with about a 21% increase in the value of the electricity. And this is for something that cost me about 8% of the cost of the plant. So the conclusion appears to be that this is a pretty good economic choice to make. So where is the technology? What's the technology basis? Well, basically, we've done it. It's been demonstrated in a small power plant on the Solar 2 facility that was operated in the later 1990s. It was a very well instrumented demonstration plant, showed 24-hour electric generation, exceeded its performance targets. It was shut down when the demonstration was complete. It's just a little bit small to be a viably economic power plant, so we did not continue operating it for that reason. The key component, the most difficult component to make, is the receiver panels. This is where the highest temperature occurs in the plant, where the thermal flux comes in and heats the salt. These pictures show the fabrication of that unit, give you an idea of what those panels look like. They're hoisted up to the top of the tower and then ring the top of the tower to receive the heat. So where can we go from here? We've demonstrated it. We're ready for our first commercial plant, and then going into hybrid installations with fossil to lower the cost of the electricity, or the large standalone plants with maybe several of them standing next to each other. The heat could also be used in other processes. I've talked to people who are interested in doing desalination with this. Process heat, this shows cement making capable with our high temperature heat. Hydrogen production from water or methane is also another application. My preference for the next step is a 50 megawatt electric plant. This would be a 3 times thermal power scale up of the Solar 2 plant. Probably the best approach is to go with 7 hours a day of generation, 4 hours of thermal storage that would give us a generation midpoint of about sunset and probably increase the value of our electricity. We could also do a 24-hour-a-day plant at 15 megawatts electric. It takes a little more thermal storage, but I just keep saying that's pretty cheap. And this is a plant that we probably will be building in Spain in the next few years. This takes about 275 acres, about 300-foot tall tower. About 4,000 heliostats are required for this plant. Briefly, the hybrid idea is an interesting possibility that will allow us to go down the cost curve a little bit faster than what the standalone plants. What we're talking about here is putting our solar heat into a fossil plant so that the fossil plant can basically generate more electricity with no more emissions. We can put the heat into the gas turbine cycle. That gets the maximum thermal efficiency advantage. It's a little bit difficult to do because off-the-shelf gas turbines are not designed to do this sort of thing. We can put it into a steam bottoming cycle. This is real easy to do from an engineering standpoint, and probably is the logical way to go. We can operate this plant as a power boost, take advantage of the extra power that you can get out of the turbines in the plant above their nameplate rating, or in a fuel saver mode where we cut back the amount of fossil fuel we use and generate the same amount of electricity. Both modes have their advantages. So why aren't we building these plants all over the place right now? Well, the problem right now is the initial first-of-a-kind plant costs. The green line shows what we believe to be a cost reduction curve that's achievable. That's not my data. This is from a survey done by Sergeant Lundy under a DOE contract a couple of years ago. They show that the power tower plant could be built for about 12 cents a kilowatt hour. Actually, I think right now it's going to be a little bit higher than that for the first plant, but it shows that we can bring the cost curve down to the 5-cent region by about 2020. But what's really the independent variable isn't time, it's deployment schedule. The faster we can build these plants and deploy them, the faster we can come down the cost curve. I've put on this chart a couple lines across there that represent the California market price reference for natural gas, gives us a comparison to what is economically viable. Last week, the price in California was $7, which means that we would have to be down about 10 cents a kilowatt hour to be economically competitive. But you can pick your number. There's a lot of disagreement as to what the price of gas is going to be in a few years. The strategies for bringing the cost are already fairly well, are really fairly well established already. We know where the cost comes from. The chart on the left here shows that 43% of the cost of the plant is in the heliostats. So that's the key thing to attack to bring the cost down. 18% is in the receiver system. That's the next thing we need to work on to bring the cost down. The rest of the plant gets to be fairly conventional and has already had a lot of cost reduction work put into it on fossil plants. So we expect to come up with our 2/3 cost reduction in the capital cost of the plant from 16% technical improvements, doing things smarter, better, 33% bringing the scale of the plant up from the say a 50 or 15 megawatt electric plant to a 200 megawatt electric plant. 200 is about as big as we think we want to go. What happens at 200 is that in the optics area, there get to be some things working against you. Your heliostats get farther and farther from the tower. Your losses get higher. And that starts to compensate the economies of scale that occur in the rest of the plant. And 18% cost reduction in volume production. If we can get a number of these plants coming online sequentially, so we've got factories putting out heliostats, putting out receivers in a very efficient way, those costs will come down too. Okay. Right now the market is very much an international market, not very much a U.S. market for power towers. I spend most of my time talking with people outside the U.S. and really very little talking with utilities inside the U.S., though that interest is picking up a little bit. It's gone from probably 0 to, well, at least they're thinking about it, but it'll take a while before their interest becomes real. Where I think we're going to have 2 plants online by 2010 is in Spain. In Spain, they've enacted some very good incentives for large-scale solar power plants. There are probably a dozen power plants in development right now, at least there were in spring. One of those will be a power tower, usually called Solar Trace, and that's planned to be a 15-megawatt electric plant for 24 hours a day. We're discussing supplying the receiver for that plant with Senair, which is the project developer. In South Africa, Eskom, which is one of the largest public utilities in the world is committed to putting online a 100 megawatt electric power plant. That's a pretty good size scale up from Solar 2, a factor of 10. I have a little bit of discomfort with that. We've agreed with ESCOM to go through a process of designing the receiver for that, then doing a test on a scale down panel to bring our confidence level up to the point that we feel that we can go ahead with a 100 megawatt plant with very, very low risk. That will have enough storage to operate 16 hours a day. And we should be working on that receiver design starting in the new year. So, thank you very much.
Right on time, and so we have time for a couple of questions.
Michael, there is no, as far as I know, no conceptual difference between storing thermal energy that is produced by power tower or by trough. In fact, there are trough plants that are now being built in Spain that includes, although, so this just goes back to your slide, trough and power tower equivalent as far as thermal storage is concerned. The only difference may be the temperature of the storage, the thermal storage material.
You're right. There's Solar Millennium project is trying to introduce molten salt storage on a trough in Spain. It hasn't been done yet. Of course, they've got about half the delta T, so their storage costs about twice as much. They're also transferring heat from the oil in the field to the salt storage, back to oil before going into the power plant, and so there's some losses in that process. But yeah, hopefully they'll be successful in making that an economic process.
You have a question over here, please?
Yeah, I wondered if you could characterize the operational issues a little bit more. For example, in the plans that you already anticipate or in the future business plan that you seem to characterize, what are the O&M, what do you see as the O&M role of Rocketdyne or the supplier that you put on there? What are you prepared to put your balance sheet at stake for in terms of performance guarantees, and how long?
We would provide typical power plant equipment warranties for the receiver, the thermal storage system, and continue to support the technology as it's implemented. It's very important to us, especially on the first plants, that the power plant operator be successful in making this work. When you're doing first of a kind, second of a kind, failure is not a viable business option. Just like we can't launch people into space and consider failure as acceptable with these power plants in the first few ones, failure is not acceptable.
One last question.
Yeah. Can you comment on the energy density thermal storage compared to some of the other technologies that were mentioned in the previous talk?
Density in terms...
Energy density?
I guess density in terms of...
BTUs per cubic meter?
No, I really don't have that sort of number in my head. As I mentioned, one of the key issues, I think, in choosing the storage mechanism is going to be based on your efficiency, your round-trip efficiency. And thermal storage does not look that good if you've already got your energy in the form of electricity. But it is really good if you've got your energy in the form of heat to begin with.
Well, thermal storage also depends more critically on the temperature differential than the mass.
Sure.
Yeah.
At a stated number.
Sensible heat.
Okay, so thanks again, our speaker, and we're going to move on. Our next speaker is Carl Rabago, Group Director, Clean and Renewable Energy, Houston Advanced Research Center, and he's going to talk about nanotechnology's role in accelerating the hydrogen economy.
As we sit here this week, much of the fuel cell and hydrogen technology industries are gathered in Palm Springs as something called the Fuel Cell Seminar. It's a big event. My technical experts and program managers are there now trying to gather the latest intelligence And I was the guy that didn't get to go. So you're getting the B team and when it comes to the technical expertise. But I can save questions and get them to the experts later. This particular presentation has been carefully timed to exhaust my technical understanding at about the time the slides are finished. So we'll see how it goes from here. And let's see, use keyboard below to advance. Good. All right. I'm from the Houston Advanced Research Center. We're a 501c3 not-for-profit contract research facility with a mission of advancing sustainable development in the greater Houston region and throughout Texas. What that basically means is that we work, we want to save the world, but we also do deliverables. And that makes us a little bit different, and I'm not going to go into the details of that right now. In our energy field, we have 3 big initiatives going on right now. We're working on something called the Southwest Biofuels Initiative, looking at biodiesel. We are the Gulf Coast Regional Application Center for Combined Heat and Power under a Department of Energy, State Energy Conservation Office grant. And we have, for some 5 years, been running the Center for Fuel Cell Research and Applications, which is the source of the information that I'm going to share with you. Our Center for Fuel Cells is an industry-funded consortium. So we have several industry members who have joined together and asked us to conduct research on their behalf. The obvious motivation for that is cost savings. They had an itch, they needed scratching, they wanted to understand whether fuel cells, especially PEM fuel cells, were, if you will, ready for prime time, so that could inform their strategic decisions as to their roles regarding this technology. And in order to gather the data, the information, the state of the industry type assessment capability at the lowest effective cost, in a pre-commercial phase of this decision-making, they retain us for this purpose. So we have members such as the Southern Company, Chevron, Shell, BP, Austin Energy, companies that are looking out ahead, wondering if they're going to have a role with fuel cells in the fuel cell industry, and asking us to help them in supporting their strategic decision-making. As we a little bit more, we start with a base of just providing them information, sort of up-to-date information, scanning what's going on, keeping track of technological trends, figuring out if things are really moving in solid oxides, or whether PEMs are going to have a high-temperature membrane, or whether we're going to solve hydrogen storage at relatively low-pressure problems or issues, those sorts of things. In addition, we do technology reviews. And our proposal for 2006 includes this list of individual technologies that we basically beat to death. That's our job. We buy technology, we beat it to death, and we tell them how it failed. The other reason this is also up here is to give you a sense of the wide range of technologies that are out there. This is sort of the 3rd year of a pretty intensive effort focusing on uninterruptible power supplies and branching out into other technologies. The industry has moved along rather rapidly in that regard and has sort of concentrated more on that in a minute, but we're now sort of into the 2nd, 3rd wave of technologies, of individual commercial products that we're looking at for these companies, having gone through the obvious leaders, the Plugs, the Ballards, the Avistas, Rely On now. And the list is longer. When we first started this program, we could spend our entire budget on one single machine handmade by PhDs and watch it fail in as little as 80 hours. Now we can buy multiple pieces of equipment. For that same amount of money, we could buy 5 pieces of equipment that had the same power output and last 10 times as long. So the industry is moving along. In fact, in that regard, I'll skip this, save you the time. In that regard, I wanted to just characterize some of the trends we've seen in PEM fuel cells, just to give you a sense of where the technology is from a kind of non-technical perspective. Very definitely, if you came by our place, we probably have the largest collection of PEM fuel cells in any non-governmental lab anywhere that we've tested and like I said, run to death. In the short walk around our laboratory, you can see in 5 years rather rapid evolution. from our DCH Enable. The company went bankrupt just after they delivered us the unit, which is the size of, I don't know, about 2 side-by-side refrigerator freezers combined with 6 kilowatts of generating capacity, 1 kilowatt of which was necessary to serve the parasitic loads of the device itself, down to our current, the machine we just finished running to death, our Nuvera machine, which has got 7 kilowatts in a stack the size of a loaf of bread. It's been remarkable in the change of that technology, and you can really see the industry converging on where it sees its market opportunities and applying the lessons of sort of manufacturing for scale as the companies that have survived have focused on those market opportunities. There is another wave of new manufacturers coming along. They tend to be system integrators who may use someone else's stack, for example, using Ballard's stack, or in many cases, or other stacks by companies like Altair to put them together into novel sort of system solutions. But it is by and large a sort of a consolidated industry, which is kind of remarkable, imagining that, 5 years ago, Plug Power was at $120 a share, and everybody thought fuel cells were going to take off like crazy. We have seen, at the same time, I mentioned the sort of improvements in cost. It's perfectly reasonable to buy PEM fuel cells at $3,000 a kilowatt, and now probably the cost of the stack is higher than the cost, for example, of reformers. That's the reason why we're talking about this, because this hydrogen-fueled PEM fuel cells, for example, is an energy storage device that stores its energy in the hydrogen and converts it on demand through the fuel cell. So stack prices going down is useful. They are more reliable. I mentioned our DCH machine died in 2001 after 80 hours. We're getting thousands of hours out of other technologies that we've bought in recent years. Their size has gotten greatly compressed, as I've already described, and the simplicity of the machines has gotten much better as well, which means that they're easier to fix, easier to access, easier to monitor, and they're served better by their sellers, by their vendors to us. One of the major, and I use this as sort of the key example, but it's also sort of the only realistic example of where PEM fuel cells have shown up to have a potential for energy, for commercialization in the energy sector these days, and that's as UPS units, uninterruptible power supplies. In that regard, PEM fuel cells really are targeting an incumbent technology, which is batteries, so the storage fit is perfect for the purposes of this meeting. And we're talking about systems that are typically 5 kilowatts or less, but I just use an outer bound of about 10 kilowatts of capacity. And that's, a small room full of batteries if it's lead-acid batteries, such as used by the telecommunications industry. In a fuel cell, it's now to something the size of, let's say, this podium plus a stack of about 6 to 12 standard hydrogen cylinders, like welding cylinders that people use. The reason why PEM is looking like a winner, or at least a competitor in this sector, has to do with power density, getting more power out of less space so these things can fit in with current installations. I think I confused, this should have been kilograms per kilowatt. Again, testimony to the fact that I'm not the technical guy, but basically you're getting fewer kilograms per kilowatt. They're getting lighter weight. Interesting things happening, for example, in our Nuvera unit using metal foams as a bipolar plate material to improve surface area within a confined physical volume. Lower maintenance, I already mentioned. A more uniform power curve than batteries. It doesn't decline with the batteries. It stays high as long as you feed it fuel. And a better environmental footprint, obviously, if you're not using something like lead-acid batteries. So those are the things that have got companies like Plug and Ballard and Nuvera all pitching an alternative to batteries through PEM fuel cells. There are issues still to be worked on, in spite of the fact that some of these units are selling commercially now. They include reliability. I don't think I've actually seen an 8,000-hour stack yet. And, of course, the old DOE standard is a 40,000-hour stack. That's based on the rather, I think, hypothetical notion that a fuel cell could propel a vehicle all by itself. And we're probably a long ways away from that. But we have seen upward of 3,000 hours in a stack. And when you talk about an uninterruptible power supply that delivers its value in 8 to 16 hours per year, that level of reliability is pretty good. Although it's got to be improved for the sort of the market niches to expand. I've discussed cost, and cost is okay at $3,000 a kilowatt, but obviously that's a pretty high number, so it's got to continue to improve. Efficiency, just again, sort of standard for any kind of energy solution. Fuel storage, because it's hydrogen, is a critical issue. I'm not going to talk much about hydrogen, a few more comments a little later on. But since I'm a veteran of the Rocky Mountain Institute, and since ultimately what matters is the work you have to do, and savings and efficiency, for example, at the point of the work done, multiply upstream, one of the most cost-effective way to address the hydrogen problem is to make more efficient fuel cells, right? You know, so if the fuel cell itself isn't more important, you can afford higher cost in your hydrogen. So it just works upstream that way. Mean time between failures is an issue, especially with stacks. Most of them are in series still. So if you have an 80-plate stack and you lose one plate in the middle, or it finally goes, then you've lost your whole stack. And unless the system has been designed for sort of hot switching, like the rely-on units, which pay a huge penalty in terms of weight and volume for that benefit, then you have a problem. So operating life is critical. And then fuel quality sensitivity, while it is greatly improved, still has a long ways to go. These PEM units are highly sensitive to poisoning by carbon monoxide, by sulfur, and since most of our hydrogen fuel today comes from reforming, and especially if the reformer is small, there's a risk of that poisoning, meaning every unit has to carry some amount of subsystem design to maintain the purity of the fuel cell. So all those are the fuel source. So all those issues remain on the table. Now, when we look at sort of down at the conversion levels, a couple of areas of technology show up as being rather important. Catalysts, both at the anode and the cathode side, and these last three bullets sort of give you this sort of terrible catch-22-ish kind of problem that comes up with fuel cells. At the one end, you can take something like platinum group catalysts and get high efficiency and sort of high activity with them, but you pay a penalty in terms of high cost. So if you're going to use it, you want to use it very sparingly. That's a challenge. So you could switch to alternative catalysts, which are lower cost, but they're easier to contaminate, which means you can lose that series stack of cells. So then you heat them up a bit so that you can kind of increase desorption of any potential contaminants across the catalyst, and that makes you pay an energy penalty. So then you go back and say, well, maybe we'd be better off with the expensive stuff again, and it goes on and on. So leading toward the nanotechnology question, you're going to see in a minute why these things might be, nanotechnology may help us out. I mentioned I'd say a couple words on hydrogen. Just, reminder of everybody, this is a standard fuel cells comment. Hydrogen is an energy carrier, so it is actually the storage device for the energy that is converted in a fuel cell, and there's all those other issues about where do we get it and how do we get it that have to be dealt with. It's dang expensive now with gas where it is. Just running our little 5-6 kilowatt Nuvera was costing us $1,000 a week, full-time operation, so that was pretty expensive. Obviously, we know the problems of storage and handling. A lot of them are related to its low density. Purity is critical, as I mentioned before. And as an example, that's why a lot of people talk about things like methanol, a highly reactive fuel that doesn't have the carbon-carbon bond, so it's easier to make use of in a fuel cell, and the liquid nature of it makes it easier to handle than that very, sort of lightweight gas. But since we don't have catalysts designed that can take advantage of liquid methanol, we have to, again, pay a heating energy price in order to vaporize it to use it in methanol fuel cells. So, example of the problem. The electrolyte, the thing that sits between the plates, is obviously an issue. The old-style conventional units, alkalins, phosphorics, molten carbonates, all used basically a hot, corrosive material, and there's a whole bunch of engineering and manufacturing issues associated with that. So PEMs tend to rely on solid-type electrolytes. Nafion is the market leader, but it's dang expensive. There's really only one provider. It quickly degrades if you don't hydrate it just right. And material quality obviously is a concern. You want to have a uniform, capability across the whole membrane. That's why some people are looking at crystalline structures called solid oxides. Those, of course, need a lot of heat. It desorbs impurities and handles carbon kind of fuels, but it needs a lot of heat. So unless you're taking advantage of the high heat waste product, you've got a high cost alternative. I will say the federal government in the last couple of years has sort of put a lot of its bets on solid oxide. And we haven't sort of been very successful in getting one of those machines successfully from a vendor, but I won't name them by name. So where does nanotechnology help? Well, a whole bunch of areas, right? Increasing the effective surface area, the shelf life, improving the manufacturing cost of the components and the materials. Miniaturization. There's one company called Nanofusion that's making micro pumps to put inside fuel cells to move methanol and water through the reaction. Membranes I've already talked about. Structure and efficiency is critical there. Tailoring your catalyst to work better. Getting systems that are stronger and that don't blow out, if you will, and a lot of work on solid electrolytes related to all of those. Why is it a good idea? Well, of course, since every molecule of catalyst energizes several other sort of subsequent activities, you get a multiplier effect from improving the performance of your catalyst. So it's a good place to go in terms of improving your systems. Strength is important because you do have flows across these membranes as well as internal strength. We don't really have any ruggedized fuel cells yet. You can't just sling one in the back of a truck and use it as an energy alternative for people working out on road crews. So as a result, we all breathe the noxious fumes of gasoline-powered weed whackers and leaf blowers. Microscopic strength critical also, and would be a great opportunity for nanotechnology to apply. Better materials might allow us to be tolerant of the fuels or fuel impurities better. PEMs generate heat. All fuel cells generate some amount of heat. Rejecting that heat effectively would be valuable. So some nanotechnology work for passive heat management would be, or energy handling would be good. I throw this last one in just because it's kind of fun out there. Altair is out working on photocatalysis. The direct solar just plus water goes to hydrogen, trying to shortcut some of the processes. There may be some help there, working at a small scale, but more to be done. One exciting example, they've just issued some press releases in the last couple of weeks just to give you a practical example of how this nanotechnology can help in fuel cells. Again, sort of at the bottom end, the place where you're really converting your hydrogen into energy is with Pacific Fuel Cell. Don't have any stock or anything. It's just a good example that I found that I hope would make me sound technically credible. So the example, as you can see from the little diagram, is you take some carbon nanotubes, you figure out a way to put platinum and distribute it as evenly as possible across the carbon nanotube, so you use it as a sort of a substrate. The alternative, by the way, the traditional alternative is using carbon black. And that's a structure which is difficult to get your catalyst distributed uniformly across, and which has a tendency to break down under sort of the mechanical and thermal activity across the fuel cell. So then you basically squeeze these things through a nylon filter to get them all stand up straight, as you can see here, orient them on the Nafion, and then kind of squeeze the whole thing together with anode layer of high area carbon. And these guys say you get better catalyst availability. It seems to make sense in a physical sense to me. Lower catalyst cost because you're using it more effectively, and longer life because you're no longer using carbon black as a substrate. As I said, that is timed carefully to exhaust my capabilities, but I'll fake an answer if you have any questions. Thank you for your attention. Any questions?
Time for a couple of questions.
I blew you away. Gary.
Just on the previous slide, was the specific fuel work done or applied to the commercial Nafion? Is that
Yeah, they're still using a commercial Nafion membrane, but their work is basically in dealing with sort of the interface. This is called in the business the MEA, the membrane electrolyte assembly. And so what they're doing is using the carbon nanotubes as the interface between the boundary of the membrane and the anode itself in order to effectuate a good transfer protons on the anode side, and oxygen on the other side.
And they just bolt it down on the end.
Yeah, they basically do. They squeeze, it's just, and then press it together. It ends up being a very thin layer that goes, and then you build those are the stacks that you stack up.
Other questions?
Yeah, in the oxide fuel cells, are the catalyst concerns pretty much the same as in PEM?
Well, because some of these units are operating like 600 degrees, you got to use catalysts that are sensitive to that, but you don't have the poisoning problems because you tend to be able to burn things off, and you don't have as much poisoning problems. So that's one of the reasons why the DOE and the military were sort of excited about solid oxide. The high temperature would produce a benefit. And everyone who's doing solid oxide seems to be talking about having a cogeneration capability, a combined heat and power capability to make use of that heat. You pay a penalty for that, of course, because you got to ramp the system up. Just like the molten carbonate units, you tend to want to keep them running when you run them. And then, of course, you avoid the molten carbonate problem of high temperature corrosive electrolyte, but you're still having to keep it on and running the whole time. So it's less problem because you get less poisoning, more penalties on the other sides.
And follow-up question. Our previous speaker indicated hydrogen would be a storage technology. I assume that means you can convert it back into electricity. Is the fuel cell the best and only way to do that?
To convert hydrogen into electricity?
Right.
It's probably one of the most efficient that I've heard of. I'm not sure there's, ICEs tend not to run well on them. I think fuel cells are regarded as the most efficient way that we've got available to us right now. Trying to think of anybody saying there's any better way to use hydrogen. I can't.
I gather then that, though, is an effective route for converting back into electricity from hydrogen without too much of a penalty. Is that the conclusion of the point?
It's always that annoying law, the second law.
Right.
Well, yeah, the issue is how much can you separate the protons from the electrons. So a typical PEM membrane has 85% separation capacity to 90%. So I don't see any other way other than a fuel cell if you want to get electricity from hydrogen storage. You may make a fuel cell with a 98% efficient membrane, but I think that's the technology of choice for storage to electricity.
Yeah, sure.
All right, thank you for your attention.
Thanks, Ken. And so our last speaker of the section is Dr. Jacob Carning. He's professor of environmental science and engineering, environmental science and energy research department, and the head of the energy center at the Weizmann Institute of Science. And he's going to talk about storage and transportation of solar energy.
Okay, let's go with immediately to the fundamental question. We see how the use of energy, the consumption of energy, is divided between sectors. It's roughly 1/3 for transportation, 1/3 for electricity, and 1/3 for thermal applications in industry. In the United States, it may vary in other countries. In Israel, you have more electricity because we don't have heavy industry. This means that if we're going to solve the energy problem, we can't just solve the electricity issue. We have to deal with the entire problem, including how we are going to generate energy to run motor vehicles or heavy industry. I think that there is an approach that may say, okay, let's use electricity for all of these things, but I'm going to talk about this a little bit. I'm not sure that's going to be possible. This is sort of like an orientation slide to show you where I come from, or this is the world of concentrated solar thermal systems. Michael have shown some of these pictures. There are basically three technologies to concentrate solar energy: power towers, troughs, and dish concentrators. And if I'm going to start telling you what I think about each one of them, then we'll never get to lunch here. Let's look now at electricity generation using concentrated solar energy. Not necessarily solar thermal, but concentrated solar energy. On the left, you see a process that is the fundamental of solar thermal energy consumption. We have a source of energy, of solar energy, that is concentrated into a device called solar receiver. There, the light is converted to heat, and that heat drives the engine. I purposely do here a turbine engine, not a Stirling engine, and we can discuss that later. The neat thing about this system is that you can always have this integrated with a combustor. So when you don't have enough solar energy, you can run the system on fuel, and you have hybridization that solves the problem of supply per demands. I spoke about this last year in a little more details. On the right side, there is a different technology using concentrated solar energy with combination of photovoltaic. The idea here is glass is always going to be cheaper than photovoltaic materials, and we want photovoltaic material to become more and more efficient. It is not reasonable to expect the most efficient photovoltaic materials to be also the cheapest. If somebody finds that, that's going to be very difficult. In fact, we're going into multi-junction cells that are going to be more and more expensive. So let's assume that I have a photovoltaic cell that is 100 times more expensive than the common silicon cell, but I use a concentration level of 1,000 times. So the price of the cell becomes low relatively in the system cost, and I can use this for high efficiency. In a minute, we'll talk about it again. Back to the solar thermal process, and I added this slide after a discussion I had yesterday with one of the people in the audience here. In the solar thermal process, you basically have three major elements. You have an optical system, a receiver reactor system that converts the concentrated light to heat, and then you have a heat engine or fuel cell. A fuel cell is an engine. It gets fuel, gets work, fuels in, work out. Now, the first two, the optical system and the receiver, are the addition of the solar system to the process. They have to be our fuel equivalent. Their cost should be similar to the cost of fuel if the solar system is to be competitive with the fuel system. So to calculate the fuel equivalent is a fairly easy process. It was so easy I didn't even need a student to do it for me. And you see right away what I shaded here in yellow is the important parameters. Right, the numbers don't mean anything. I wanted the nice numbers, and that was done only a few months ago, where about $5 per million BTU was a reasonable price of fuel. And now we all know what happened with Katrina. But it doesn't matter. I can easily fix this, I guarantee you, for any value of fuel. But the point to see is the parameters. And apparently, the three main parameters that I looked into here is, first, the cost of the receiver and reflectors, as was pointed out by Michael beforehand. Another one, that's the third one, is the input. It is the cost of solar energy is going to be much lower when you go to a really good site. If you're going to try and put this system outside in Houston, you're going to pay a lot of money and you're going to get very little out of them. The Germans are using solar energy somewhere in Leipzig, where I think the number of sunny days a year are about 6. But you can always you can always pay for that. Another very important parameter is the optical efficiency. And I made a drawing of it on the right, and you can see how the fuel equivalent cost is going down as the optical efficiency goes up. Optical efficiency turns out to be a really important parameter in all of those three systems that I've talked about before, the trough, the tower, and the dish. Now, what do we need to do? We need to increase optical efficiency. We need to make receiver and reactor that can match the best engines, and we've got to develop new engines, okay? And I salute the fuel cell people. We can work with them. Fuel cell is a type of new engine, not the only one. The problem we've had is always you try to take existing gas turbines or Stirling engine and retrofit them to work with solar. It's not the right approach. And I can explain later why you can't just take a regular Stirling engine and make it work with solar. It's a dream. It can't happen because of thermodynamics. Okay. The story is a lot simpler with concentrated photovoltaic. What you need is to make a more efficient cell. And it doesn't matter what it costs because I can always compensate with concentration. And I have to cool. So here is what SpectroLab is telling us how the efficiency of solar cell is developing. It's remarkable. They have announced that they got to 40%, and they're going to go up and up and up. I think that there are also other companies around that are claiming they can get to over 50% efficiency of solar cells. This is very nice. It's just a matter of a material study, and they are not cheap. And they have to, and the grid of the current carrier has got to be very thick because we are putting a lot of photons concentration on these things. The key, again, is system efficiency. You've got to cool these guys intensively. We've got to do it cheaper. But if I can look around, I think the concentrated photovoltaic is the fastest growing area within solar energy. More and more companies and research are popping out. Okay, it's done with the introduction. Now, storage of solar energy. And of course, if I'm going to give a negative example, being a solar guy, I've got to do it with wind. So please forgive me. Solar doesn't fare much better than here. This example was given to me by a large utility in Germany. And I've got one in the next slide, is a utility from the United States. They have a hard enough time trying to match the load, as you can see on the upper fluctuation wave, using normal procedures. In come winds, totally unpredictable. What are you going to do? Okay, there are two solutions. One solution is put as little wind as possible so you can just carry it with the noise. The second thing is you can't do that because the government says we have to put more and more. In Germany, they're going to have 20 or 30 gigawatt of wind, 25% of the total, this is the plan of the total consumption. What are you going to do? Well, they have no other way but to put what they call a shadow plant. First of all, they've got to build a wind plant because it's there and they're paying little money. They're not making a lot of money out of it. Then they have to put another plant that produces literally all the energy that the wind will produce, but it works only when you don't have wind power. It may be 5% out of the year or 50. Their shadow plant is a real loser, and they have got to absorb the cost. The more wind they put in, the more shadow plants they have. So you can think what you can try to imagine what these people think about wind power. Okay, this is an example from Arizona. Basically, it's the same idea. When you need the power, peak power, the wind gives you only 11% of what you need. I don't think utilities like this kind of balance. So, what's the solution? Well, to be honest, put the curve of solar in here without any hybridization, without any storage, as Michael was showing, might be a little better. It's still going to pose a problem if it's a large part of the load. So, conclusion, well, we must provide energy per demand. So hybridization with the solar thermal is one way. Storage and transportation are also required because we can't just be satisfied by equalizing the load, we also have to drive cars with solar energy or wind power or whatever, or use it for industry. So we have to develop method to store and transport solar and other intermittent energy source. Now, before I go further and we talk about storage of energy, I want to make a classification of energy that's stored. There are two, let's categorize energy into two categories. One category is in a form that is or equivalent to heat, and the other category is a form that is or equivalent to work. Okay? Now, there is an annoying law between the conversion of heat to work. It is one of the most unpopular laws of nature, and it continuously interferes with the Disney law all the time. But it's a fact of life. Solar energy, as it comes from the sun, sunlight, fuel, thermal energy, are all in the form of heat, or equivalent to heat. Wind power, electricity, are a form of work, basically. So if you're going to store wind power or electricity, going back to something that is a form of fuel, you've got back that annoying law in back conversion, and you're not going to win. Now, I know that economics law matter a lot more than thermodynamics law, but some of us still believe that good thermodynamics would eventually lead to good economics. So, please, I don't think it's a good idea to take wind power and convert it to fuel and then go back to work. Okay. Now we're going to talk about the way to store solar energy. Now, solar thermal energy, I'm comfortable here because I can store it as heat or as a form of heat. A fuel is a form of heat. It's an elegant form of heat. It is, first of all, we are used to it. Everyone knows what fuels are. Secondly, it is transportable. It is some of the fuel. It can be stored and can be used. What are the restrictions that we want to put on it? It has to be clean. Otherwise, we put part of it, clean environmentally. Otherwise, we solve half of the problem and create another problem. Fundamentally, and again, this slide I showed you last year, this is the general concept. You have a certain material that has low heating value. It's a lousy fuel or it's a no fuel. You put it into a chemical reactor and introduce energy and create some kind of an endothermic reaction. What comes out is another material that has higher heating value, defined as fuel. Take that energy and that fuel and burn it or use it in some kind of reaction in your engine, out come work, and back come the material that you started with, that is the reactant. Take that back into your solar facility or power plant, whatever it is, and keep on working. This way you're not polluting. This is the main concept here. Conceptually, it looks very nice, and now comes a lot of questions. What materials can be stored and transported safely and cheaply? How are we going to do this, and so on? So there are many ideas. The first idea was, of course, to split water. And if you don't remember, the person that suggested the splitting water process was none other than Jules Verne. And we all know that he hasn't been around for some time. Actually, he said it in 1873, I believe. He said that they had a big problem with coal for heating in the big city. He said, fellows, water is the coal of the future. Nothing to worry about. People will be smart enough to split water in the future, and it'll be very easy. I think we let him down so far. Anyway, these are some of the processes that are being tried to create fuels in a clean method. Now, you don't have to remember all of them. I'm going to go over some of them in a little more details now before lunch. But fundamentally, water splitting, and it's not easy, and we can't do it directly. It's been done directly, by the way, in the 70s at the University of Minnesota by Professor Ed Fletcher, and repeated by some others. But it's at such a high temperature that it doesn't, it was done at about 3,000 degree K. It's not very useful. Remember the optical efficiency. Another process, metal reforming, is the main process used now to make hydrogen commercially. In Germany, there was a project called Adam and Eve in the 60s to do exactly what I'm writing here in the second process of the metal reforming with CO2, going back and forth, and you take methane, CO2, add to it heat. They propose to do it with nuclear. You get syngas, and the syngas you run to the plant, use the syngas, the heat from the syngas by a reverse reaction going to the left, and you get out back the CO2, the methane and the CO2, run it back to the plant. The solar people, all that we did, we said, okay, we can't do it with nuclear, let's do it with solar energy. And a lot of work has been done on this process. The next one is to take a metal oxide. You can take a metal oxide, maybe we can split it or reduce it, take the oxygen out. Now we have a nice, easy form of transportable material that can be, and the reaction can be reversed and run back to the plant. And then there is the hydrogen and methanol issue. The last two, actually, the biomass is obvious. Biomass is a negative value. Take the carbon from the biomass, or take biomass, do pyrolysis, do gasification, and you got the syngas again. But the last one and the third from the bottom, the hydrogen and methanol, the CO2 process and the photocatalytic reactions are my favorite, and we'll keep them for just before lunch as an early dessert. Okay, let's start with the thermochemical water splitting cycle. It was said that the problem with the old people is that they already thought about everything. So in the 1970s, there was the first hydrogen mania that grabbed this country, and $6 billion was spent. And much of the money went into, not only here, in other parts of the world, into developing thermochemical processes to split water. Essentially, you split water by using a process that has several steps. Later, Brown, Funk, who was one of the most active people at the time, and others were asked to summarize all this. They took the best 115 processes they could think of, there were more, and they found a way to grade them, and here are the top 10. Okay? None of them came to use. It was explained yesterday by Ash that in Sandia they are now using number 4, the sulfur iodide process, so let's look at that one. And as much as I tried, I didn't balance it. It's not balancing it, I'm sorry. But basically what you have, you start with two reactions, one at a higher temperature, the other at a lower temperature. One is hydrogen sulfide and iodine hydride, and you run them through an endothermic reaction, producing the other materials, and then you go on with that, and eventually the net process is that you take water. In the last step here, you actually, you have to add water all the time, and this is where I didn't, you need some of this water here. This is not enough. You have to add some water to the process here to make it going, and then you just, water is basically being produced into hydrogen and oxygen. This is one process. I used that one. I only made that slide last night because it was discussed yesterday. The sulfur iodine process is being using Sandia. It's not, in my mind, actually, you know, other processes got some higher grading. I don't know if 78 is relative to 80 it makes a difference here, but there are some attempts around the world to continue to work on these processes. Okay. Now, before we go on, let's look at some energy content or energy concentration, and the question was asked before. Where are we now? So gasoline has a very high energy per mass value and very high energy per volume. This is the problem. We are against a tough competition. And in all likelihood, the fuel we're going to have is not going to be as good as gasoline. Our gas tanks are going to grow. But maybe it's a price we're willing to pay. Which one is coming close? Well, the LPG and the LNG are good, but the process of making them is extremely expensive, as Greg said earlier. And the next one in line are the methanol and the ethanol. Now, ethanol was tried in Brazil on large scale, semi-successful, and one of the main conclusions, and in this country here too, one of the main conclusions is, let's use methanol, not ethanol. There is some problem in the conversion of ethanol through the fermentation of here is corn and there it's sugarcane in Brazil. But methanol seemed to be, there are more and more people who are coming out of hiding after that big wave of hydrogen to say, hey, methanol makes more sense than hydrogen. And when you say this, you say, you think so too? I always said that. And this is the kind of discussion that go on. It does make more sense than hydrogen. Methanol is a liquid. We don't have to change any of the infrastructure. My grandma can easily pump methanol in the car. How is she going to do it with hydrogen? So let's talk a little bit about methanol later. On the right side, we say, I'm going back to the metals oxide issue. So you got to figure out which metal to use. And we've tried iron, we've tried zinc, we're working on magnesium, and we're going back to boron. Boron, looking at the element table, has got a better heating value, a much more higher concentration of energy per unit mass than all the other metals. And it's available in nature without any, it's widely available. It's hard to make, there is no real industry to make large-scale boron. Needs to be done. So here is what it looks like. I could have drawn that nice scale with the colors that I did before, and I will show some of those later, but now let's get real. This is what you have to have. You have to have a solar plant. In this case, in the solar plant, you will make magnesium, because the way to make boron is to make magnesium that will then reduce boron oxide. You can make magnesium either by electrolysis or by a thermal process using hydrocarbon. So here we chose to show the electrolysis. The magnesium then go to a boron plant, the processing plant, and then the boron is reduced by magnesium, and you have boron. Whatever goes back to the solar plant goes back to the solar plant, whereas the other processes are being discharged, heat is discharged, and boron is brought to the fueling station as powder. There we can go, put it in our car. In the car, there is a reaction between boron and water, producing heat and hydrogen that then are used to drive the car, both heat and hydrogen. And so that's the process. And when you go and you say, without trying to be true to yourself, the efficiency from sunlight to the work that the car engine is produced, you get to something about 10%. Putting things in an optimal shape, you know, there are going to be losses in the way, assuming sometime we'll perfect this process. Is that a lot? Is that a high efficiency? Is that a low efficiency? I don't know. But this is about what you can expect, not better. And this is the best of the metal oxide processes. Okay. This is one of my favorite. CO2 is the evil, right? CO2 is the bad guy. Why don't we use it as fuel? Let's use CO2. People are talking about sequestering CO2. Hell, it's a lot easier to take that CO2 that we are going to, we're not going to let it go out to the atmosphere, no. We're just going to grab it and put it back as a fuel. And CO2 can be reduced to CO. CO is an excellent fuel. It was used as a fuel in the early 90s. You can make methanol with CO. You can make hydrogen with CO. I like methanol. Okay? Take the CO and add water to it after you produce it and make methanol. Drive the car with the methanol. Don't let the CO2 go out. Grab it again and take it in the plant. Neat cycle in my mind. What's the problem? It's not easy to reduce CO2. And we're working on it. It can be done. You need high temperature, and the trick is to go down with the temperature. I think that my colleague, Dr. Floman, who's sitting here, and I talked about that, and this is the main challenge, to how to lower the temperature of the CO2 reduction process. And the last one, okay, that's now all the bright students from Rice. I wanted to just go get your passport ready, come work at the Weizmann Institute. I need somebody who can show me how to do this process. And the reason it hasn't been done, it needs 3 disciplines. It needs those solar guys like, say, myself, that can concentrate the light and make engine with them. It needs the photocatalyst guys, and it needs good chemists. Okay? So I'm looking for those guys. This is the challenge. This is the holy grail. If we could do what the trees are doing all the time, but at a higher efficiency, and we can get the higher efficiency if we get higher concentration of photon in the process, and we keep on taking the product out, keep on taking it out so the process continues at a normal kinetic rate. If we could do this, this is a wonderful process. I think nature will be happy too. I mean, we're going to do what nature is doing. Okay. Bingo, 12 o'clock. Future work, what do we need to do? We need to improve the solar electricity producing mechanism we have, and we need to develop method to store and transport solar energy. And I propose a few, and I think there are probably other out there that maybe haven't been thought about yet. And if we really want to find them, we should see what the old people said. Jules Verne and the other guys, they had some good ideas. And this new research can really lead not only to cost-effective electricity production using solar energy, and some nice numbers are coming out from the calculation that Rakuten is doing, from what we are doing. Solar, thermal, and concentrated photovoltaic, and thin film PV can get really nice numbers in terms of cost, and they look better as the cost of fuel goes up. Energy storage via clean fuels makes sense to me. High efficiency fuel cells, solar cells, and biomass gasification as an added process, and probably other things that can be done. Thank you.
We have time for a couple of quick questions before going to lunch.
You know, I'm very impressed by this solar thermal, and I think as a PV guy, that's a real confession on my part. I'm really impressed by it, especially the dispatchability and the fuel production. So I have a question, which I think I used to remember the answer to, but somehow can't remember. We had a spurt of subsidies that helped bring wind farms into use in California and other places that helped bring down the cost of wind farms. Now, I remember that the big problem with solar thermal is you have to build a big system. And so when we weren't really that energized about climate change and things like that, we weren't putting in these big systems, and so PV was growing, but the solar thermal and other big systems were having a hard time. Why didn't solar thermal, the power tower, the troughs, the storage, why didn't that take off a little bit earlier with wind So that at this point now, it would be down at 5-6 cents a kilowatt hour, like you're projecting once you get some volume. What am I missing? What was the key problem?
Wind is cheaper.
So just because it was that much cheaper?
Wind is a cheaper. People figure out how to do wind cheaper than they figure out how to do solar energy. That's just the point. I think that the methods we have developed now show comparable prices to wind and lower. But we are now where wind was in the 80s in that respect. Wind in the 80s screamed, we can do it cheaper, we can do it cheaper, and no one believed it until they did it. I think that's the main issue.
Well, you know, then let me be more direct. I mean, the power tower, for instance, looks to have everything. So, and I know DOE can oftentimes replicate a lot of the silly decision-making that occurs everywhere else, which is to say, do the most complicated thing first and the easiest thing last. So power tower got eliminated a long time ago. So I'm not saying that was, you know, I understand that could have been just a really silly decision. But why has it been so moribund for so long? Why couldn't it have taken the same pathway as wind?
There is a lot more elements in the configuration of a solar thermal system. You've got to use the right engine. Are you going or are you not going to use storage? Are you using heliostat? Are you using troughs? There was more to go wrong. We made a lot of mistakes in the systems that we built in the 80s and early 90s. We've been banging our head with those solarized Stirlings for 30 years. Why? Because Stirling is an optimum cycle. Well, it isn't. Especially not if it's solarized. You add volume. Efficiency goes as delta V over V. You add a lot of volume. It's never going to be efficient. It is not going to be as efficient as a gas turbine. Why do we keep banging our heads? I don't know. Because we started. And we can't admit that we were wrong. I don't want to start bashing anybody. The bottom line is wind made it, PV made it, solar thermal hasn't. It's not because it can't.
But, you know,
we haven't done it right.
Yeah, it sounds like there were more physical problems. That could be more things to go wrong.
Is there any work that's been done on solar thermal at a smaller scale, distributed rather than these central large? And what about the light part? Being able to light, in terms of a distributed solar thermal, you've got the potential to integrate that, say, into a building system and use it more efficiently for heating directly or to do work in some engine rather than going through the electric conversion. And then also the light that you're collecting to use it directly. It seems kind of silly. We're taking solar energy, converting it to electricity to create heat or cool or light. Why not take the solar and use it directly to do those things?
All those things are done.
They are.
They are done on various scales, small scale, large. Obviously, the more feeding system for small scale would be the dish that is smaller. A lot of people are doing both solar thermal and concentrated photovoltaic for smaller applications, say from order of a few kilowatts of electricity and combination of heat and power.
I don't see it in the practice. It's not.
No, it isn't. Part of the reason for it is that you've got to convince people they can use heat directly, and you don't have to have what is it? Heat engine to take heat and take electricity and convert it to heat. It just doesn't make any sense.
Just a quick comment on the wind to try and scale it. Wind has gone from an economy of scale. Typical wind turbine 20 years ago was 20 kilowatts. Now the standard is 1.5 megawatts. That's per footprint on the land. That's the big economy of scale that's driving wind down. A huge increase in unit capacity.
I had a question, so I decided, I figured maybe I want to get into questions.
Okay, I was talking about solar energy. How would you store wind energy? And how would you store electricity? And my answer is A, not as fuel. B, in a form that is equivalent to work. So that leads us to either compressed air, hydraulic, flywheel when they grow up, capacitor and other things, not as hydrogen. Thank you.